Differential solubilities. Qualitative analysis of a solution using the different solubilities of the cations with various anions. It is possible to have a situation in which certain insoluble substances will precipitate and others will not. Some of the rationale for this is just the reading of the table of solubilities. That is, some things are soluble and some are not. For other substances, we need to look at how much will dissolve under the conditions of the solution. This selective precipitation is the basis for many different schemes to identify the ions present in a solution. In general, these schemes are known as qualitative analysis because you are finding out what is present, not how much, which would be quantitative analysis. Let's look at one example of a qualitative analysis scheme. We see here one separation scheme shown as a tree in which the cations are separated by adding some anion. At each addition, some of the cations will precipitate with the anion and the others will not, allowing us to make this tree of separation. Generally, we will precipitate the cations that are least soluble first. Then, once those are removed from the solution, we will precipitate the cations that are least soluble of those that are left, and so on. At each step, we will need to perform a physical separation of the precipitate from the solution that remains. The ions here are color-coded to match what makes them precipitate. You should note that the arsenate ion, AsO4 3-, and the dihydrogen arsenate ion, H2AsO4-, are anions that are included because they will decompose to produce the arsenic 3 cation. You should also note that we separate the cations into 4 groups. Within each group, other reactions will need to be done to identify the specific ions present. Let's look a little more closely at the specific reactions that are used to separate this list of common cations into the 4 groups. The first reactant is to add HCl solution to the solution. The big 3 ions, Ag+, Pb2+, and Hg2+, will precipitate because they are not soluble with the chloride. But other cations will not because they form soluble chlorides. So we are able to separate those 3 ions from all of the others. This is a big help, because these 3 will precipitate with almost any anion we add, and so knowing that they have been removed from the solution makes it clearer when other things precipitate. The second reactant is sulfide. This one is added in an acidic solution. The reason for this acid-base division is that sulfide is the conjugate base of a weak acid, HS-. In an acidic solution, the concentration of the sulfide is reduced significantly because of the formation of the weak acid HS-. This means that cations that will precipitate in an acidic solution of sulfide have a very low solubility. You can determine which substances will precipitate under these conditions by solving the acid-base equilibrium at the particular pH to find the initial concentration of sulfide ion, and then using that to see if the solid will precipitate. Once these particularly insoluble cations are removed, then others may precipitate when the concentration of the sulfide ion is larger, as it is in a more basic solution. These substances are soluble enough that they remain in solution in an acidic solution of sulfide. Note that some of these will precipitate as hydroxides because the hydroxides are less soluble than the sulfides, while the others will precipitate as sulfides. Once all the sulfides have precipitated, we are left with substances that are soluble with most things. The addition of ammonia and ammonium dihydrogen phosphate allows those substances that form insoluble phosphates to precipitate, while leaving the alkali metals and the ammonium ion in solution. This type of analysis used to be very common and used to be an important part of any analysis of a solution. Today, there are other means of analysis that do not destroy a sample, like ion-specific electrodes, or use less material and can analyze for multiple ions at once, like atomic absorption spectroscopy. So this is not as important as it once was.